Welcome back to my channel. We're going to be starting Unit 2, but before we get too far into the content, don't forget to smash that like button, and I hope you subscribe for more wonderful calculus content. So today we're going to be talking about average rate of change versus instantaneous rate of change. So let's start with average rate of change. Average rate of change is the change of a certain function over a specific interval, and that interval has to be a closed interval, so like from A to B. So we're going to abbreviate average rate of change equals. So the formula that we are going to be using should look very familiar to you guys. F of A minus F of B, all divided by B minus A. This should remind you of the slope formula because that is what it is. So one of the things that the average rate of change tells us, it tells us the slope of the line through 2 points. The two specific points that we're going to be talking about are A f of A and B f of B. So generally speaking, average rate of change is done on the endpoints of our function. So generally to tell you, find the average rate of change of a certain function on A to B, and that is why we are going to be using A to B. So find the average rate of change for the following function over the interval -1, 2, 3. So what we're going to do is we are going to plug in our two things into our function. So if I want to find the average rate of change, we're going to do average rate of change equals B is going to be 3, A is going to be -1. So f of 3 minus f of -1 divided by 3 minus -1. So f of 3, we're going to plug in 3 to our function. And we are going to subtract what it looks like when we plug in -1. Three minus -1 turns to 3 plus 1. Okay, so 2 times 3 is 6. 6 plus 3 is 9. 2 times -1 is -2, plus 3 is 1. So we have the square root of 9 divided by the square root of 1 divided by 4. The square root of 9 is 3. Square root of 1 is 1. We have 3 minus 1, 2 over 4, or 1/2. So the average rate of change of f of x on the interval -1 to 3 is 1/2. On the other hand, if we have a graph instead of a written equation, we would look at it as endpoints. So -1 to 3, so -1 is right here at that 0, so -1, 0 is one of our points, and 3, 8. So I can do it either using our 2 points, or I can kind of remind myself of a slope triangle here on our graph and use that. So if we look between our 2 points, every time I go over 1, I go up 2, and that kind of follows as I go over. But if I want to practice using that formula, which is the slope formula, average rate of change is equal to 8 minus 0 divided by 3 minus -1. 8 divided by 4 which is equal to 2, which is the exact same thing that we got. So our average rate of change is literally looking at our function as a whole, looking at those endpoints of our graph and kind of connecting them, endpoints of our interval, creating this line between them and finding the slope of that line. On the other hand, we have the instantaneous rate of change of a function. So the instantaneous rate of change of a function at our interval a to b. So the nice thing is this can be a closed interval or an open interval. So it doesn't have to be a to b specifically. So like these other one, we had to have -1 to 3, and those two had to be included. This one, the endpoints don't matter that much. Is defined as the slope. So we're still looking at slope here, but we're looking at slope a little bit differently because when we're talking about the instantaneous rate of change, we're talking about a singular value. So it is defined as the slope of the tangent line at AB. So some of the stuff that I was saying is still true. We don't necessarily have to have a closed interval when we find the instantaneous rate of change. And this is part of the reason why interval notation is actually kind of hard. And that's because this wasn't actually talking about an interval a to b. This is a point. So this right here is point AB, just like that is. So, for instance, if I wanted to find the instantaneous rate of change of our function at a specific place on this graph, say -2, one of the things that I would have to do is try to find the slope of this graph that touches this line, or touches our function, but maybe doesn't touch more than our 1 point. So we get a graph, we get a line, we get a function that looks like this, and it's kind of even a little off. I just want to turn it a little bit. If only I could rotate this. But it's close enough. So one of the things that we have to know is that we can't actually find the slope of a singular point. The reason why is we rely on having 2 points to find our slope. If we were to only have 1 point and we plugged it into our slope formula, it would give us 0 over 0, which means that we would have to absolutely try something different. So we need to kind of have this discussion about a tangent line. So in order to find a tangent line, we currently have to estimate, which we know after a certain point in time is just not really helpful. So we are going to look at what is called a secant line to kind of help us out here. So a secant line is like the average rate of change. So if I have a function, say something that looks like this, our secant line is any 2 points on this graph put together. So say I wanted to find the slope between these 2 points, which could be like our average rate of change. As long as they go through both points, then we are good to go. So secant line is always that line between two or more points on our graph. Tangent lines, on the other hand, only go through 1 point that matters. It can touch more points on our graph than just the one, but only this 1 point matters. So if I have a tangent line here, or a point of tangency that I want to look at, then I'm going to look at this line that goes through here, but then also matches the slope of our overall function, but at that singular point. So what we do is we use secant lines to kind of help us find our tangent line. So in our next video, that is what we're going to be talking about. It's kind of a lot, so it may take us a little bit.